In this video, we would like to model the change in quantity by using the change in price. So we have the logarithmic transform of quantity and the log transform of price. And what we do is we try to regress the LNQ, the log quantity on log price. And we would like to have the heteroscedasticity robust standard errors. So here we see that our coefficient on the log price is negative 1.21, which means that if price increases by 1%, then we would expect a negative 1.2% decrease in the quantity. Our problem here is that between quantity and price, the causality actually goes both ways. So there is a simultaneity bias. So what we do is that we have to find, or we can try to find something which affects price but not quantity, and which is uncorrelated with the error term. So this would be an instrument. And in our case, we can use the state tax, because the state tax does change price, because it comes on top of the price and the production price, and the state tax does not affect the quantity demanded at all. So what we can do is that we can regress the logarithmic transformed price on the state tax. And what we do here is that we extract the exogenous part of the price by using the information in state tax. So in our first regression, LNP is endogenous because it's correlated with the error term because of this simultaneity bias. And the state tax, it's not correlated with the error term, so it's exogenous. And we can use this exogenous part or this exogenous variable to extract the exogenous part of the price, such that we can get an unbiased estimate of this coefficient, this causal effect of a change in price on the change in quantity. So if we run this, we have the first stage regression, and what we do is that we have the F statistic. We see that state tax actually explains a significant part of the change in price here, the log price, and we see that the t value for the coefficient is above the critical value. So what we have now is that we have we can test the state tax coefficient, and as you saw here, if you only have one independent variable, then the F test here gives the same result as the test on the single coefficient. And what we can do now is that we can predict the LNP hat, the fitted values. So now we have a variable called LMP hat, and this contains the fitted values from the regression. Okay, so now we have the fitted values, and these should be exogenous. These should be uncorrelated with the population error term. So now we can continue with the second part of the regression, which is that we try to explain the variation in the log quantity by using the exogenous variable LMP hat. And this is the result, and we always check the f-test. So the p-value for the f-test is below 0.05, which is below 5%. So we say that this regression has explanatory power. And the coefficient has indeed changed from negative 1.21 to negative 1.08. So we are now thinking that this is an unbiased estimate of the population coefficient, and we are now drawing the conclusion that if we change price by 1%, then the quantity will change by negative 1.08% in the opposite direction. Alas, there is a problem with this, because we have predicted, or we have manually ran the first stage regression, and we used the fitted values, the predicted values, in the second stage regression. And if we do this, then in the second stage regression, it treats the fitted values as observed values, which means that the standard errors, even if we have robust standard errors, these are probably biased. So we can't trust these standard errors. A solution to this is to use the function IV regress in Stata, and we just define that it should use the two-stage least squares method, and the y variable is the logarithmic transform of the quantity. And here we can define the instrumental variable. So we have our endogenous variable here, endogenous independent variable, and it should be explained by the state tax. So this defines which instrumental variable you are using to explain your independent variable. And we would like to have the robust standard errors. So if we look here, then we have the second stage regression results here, and we look here to the f-test, and we see that the model has explanatory power, so we can use the model. And we see here that the coefficient on this price is the same as in our manual regression, second stage regression, but the standard errors are a bit different. In this case, they are lower, but often they are higher. And this means that we can say that the coefficient on price is statistically significantly different from 0 because the z value here is equal to the coefficient divided by the standard errors. It's greater in magnitude than the than the critical value, and the probability of getting a more extreme result than this coefficient here is extremely low. It's 0.1%. But in this case, we only have the second stage regression results. If we would like to have the first stage result as well, then we can just add first at the end of the command line. So here we have the IV regress function. We define that it should use the two-stage least squares method. We have our dependent variable. We have the endogenous independent variable, and we have our instrumental variable, which we use to extract the exogenous part of the endogenous variable, such that the endogenous part is, by definition, uncorrelated with the error term, so we don't have any bias. And we want the robust standard errors, the heteroscedasticity robust standard errors, and we would like to show the first stage regression results. So here we have the second stage regression, as you saw earlier, but we also have the first stage regression. And here we can check if the instrumental variable is explaining a part or a significant part of the variation in LMP, and we can perform a hypothesis test to check if this state tax variable or the coefficient of the state tax variable is indeed different from 0. And we see here that the t-value is 6.35 and the p-value is below 5%, and 0 is not in the 95% confidence interval. So we say that this is a relevant instrument for explaining the exogenous part of the log price. Now there are two types of variables that we can put into our model, which will help us create a better fit, and that would be control variables and exogenous variables. Well, a third variable could be an additional instrumental variable in the first stage regression. So the exogenous variables, they are included in the regression to make a better fit, or make the model better explain the variation in the independent variable. In this case, logarithmic transform of the quantity of cigarettes demanded. And these exogenous variables, they are basically moved from the error term into the model, and they are uncorrelated with the resulting error term, and they may be correlated with the endogenous variable, or they may not. So the reason for including an exogenous variable, which is not correlated with the endogenous variable, is that it makes the standard errors lower, because it helps in explaining variation in the dependent variable. And if the exogenous variable is correlated with the endogenous variable, then including the exogenous variable in the model reduces omitted variable bias. So that would be the two types of exogenous variables that we would like to include in our model. And the control variable is a variable which is included in the model to make sure that the instrument is uncorrelated with the error term. So if the instrument is correlated or slightly correlated with the error term, then it's partially endogenous. Okay, and we don't want that, because we want the instrument to be exogenous, which is uncorrelated with the error term, in order to extract the exogenous part of the endogenous variable. So if we have a problem with correlation between the error term and the instrumental variable, then we can include a control variable. So the error term, you have to think about the error term as just a bucket or a collection of variables which affect the dependent variable, in our case the logarithmic transform of Q here. And sometimes the variables in the model, included in the model, is correlated with some variables, one or more variables, which are left out of the model, and thus is included in the error term. So that's why there might be a correlation between a variable in the model and the error term, because you didn't get data for the variable which was not included in the model, for example. So if we want to include a control variable, then we can easily do that by just typing IB regress, and our dependent variable is still the quantity demanded for cigarettes, and our endogenous variable is still the logarithmic price of cigarettes, and the instrumental variable is still the state tax. But now we have the logarithmic per capita income for the state, because we think that the income in the state per capita and the state tax might be correlated. So now we run the this two-stage least squares regression with robust standard errors, and we would like to print the first stage regression. If we give ourselves some real estate here, then we can look at the first stage regression up here, and the first thing we can notice is that we have explained the hopefully the exogenous part of the logarithmic price variable by using the instrument state tax and a control variable, logarithmic income per capita. And this income variable is included in the model to make sure that the state tax is exogenous, which means that it's uncorrelated with any variables contained in the residual term. And another interesting part here is that this control variable is included because we are thinking or we are using logic. So we are using our knowledge about economics and maybe some previous studies results to say that, well, this is probably a variable which is correlated with state tax, and if we do not include it, then state tax might be correlated with the error term, and hence it would be endogenous. So this income variable, it's present both in the first stage regression and in the second stage regression. So that's quite important. But in the second stage regression, you do not have the instrumental variable. So in the first stage regression, you have the instrumental variables and the exogenous variables and the control variables. In the second stage, you have the endogenous variables and you have the control variables and the exogenous variables, but not the instrument. So in this case, the p-test shows that, well, this instrument is explaining a significant part of the logarithmic price function or price variable, and so it's useful. And in the second stage regression, then we see that the coefficient on the logarithmic or the change in price is negative 1.14, which means that if we change price by 1%, then we would expect the quantity of cigarettes demanded to change by 1.14% in the opposite direction. This is then our estimate of the causal effect of a change in price on the change in quantity. In our model, we have one endogenous variable and we have one instrumental variable, but we can use more than one instrumental variable. In our case, we have one endogenous variable here and one instrument, and we say that our setup is, or our regression is exactly identified. But if we add one more instrument such that we have more instruments than endogenous variables, then we say that our setup is over-identified. And why should we add one more instrumental variable? It's because if we can explain the exogenous part of the price even better, then we will get a better estimate of the coefficient on the coefficient of a change in price on change in quantity in the second stage regression. And one possible instrument would be the cigarette tax, which is specifically on tobacco products. So this cigarette tax is specific for tobacco products, whereas the state sales tax is for all products. So the cig tax should probably not be correlated with any of the emitted variables which are in the error term. So the way to add an extra instrument is just to add the instrument in the first stage regression here in the parentheses. And remember that the exogenous variables or the control variables will still be included in the first stage regression. So if we include cigarette tax in our regression and it's a instrumental variable, then we can see here from the first stage regression that the p-value is saying that these are relevant, or this first stage regression is relevant in explaining the variation in logarithm of price. And we have these two instrumental variables, and we have the control variable, which is included to make sure that the state tax variable is uncorrelated with the error term in this regression. And we see that both these instrumental variables are statistically significantly different from zero. So we can go to the second stage regression, and first we check the f-test, and we see that yes, indeed, we have used the fitted values from the first stage regression, the fitted logarithmic price, to explain variation in the logarithmic quantity. And we also include the control variables or exogenous variables in the second stage regression, in addition to the endogenous variables. And we see here that if we include the cigarette tax instrument, our estimate of the causal effect of a change in price, a percentage change in price, means that the quantity, the percentage quantity, will change by 1.27 percentage points in the opposite direction. So if we increase price by 1%, then we decrease the demand for cigarettes by negative 1.27%. And ironically, this is quite close to the first regression that we did. We just regressed the logarithmic transformed quantity on the logarithmic transformed price, and we got a result here of negative 1.21 on the log price, which means that the the bias in this regression was such that it did not affect the causal effect by much. But without going through the instrumental variable regression, you would not have much faith in this first regression result. Okay, so because we have used the two-stage least squares regression with instrumental variables, we are quite confident that this result that we got actually holds.